Hi everyone, in this video we're going to go through section 4.3, linearly independent sets and bases. The term linear independence, we've seen that previously, so we get a refresher of the definition, what it means for things to be linearly independent before moving on to like more new stuff. Okay, so that linear combination of my vectors, so I'm looking right here. If I have a set of vectors, they are linearly independent if that linear combination has only the trivial solution, meaning the only solution is where C1 through CP are all equal to 0. And then that set of vectors is linearly dependent when a non-trivial solution exists. So there's some weights, not all 0, such that that linear combination is true, that it holds. Okay. Theorem 4 starts out this section of new content that says a set of vectors, a set of one or more vectors, or excuse me, two or more vectors with v1 not equal to 0 is linearly dependent. So the set of vectors is linearly dependent if and only if some vj, some vector, is a linear combination of the ones preceding it. Okay, that's what the theorem says. Now, the way that we use that theorem as it relates to our vector spaces is that now that we can talk about vectors as more than just vectors in Rn, we can talk about polynomials as vectors, right? So I have this first example here where I'm given three polynomials, p1, P2 and P3, P1 equals 1, P2 equals t, P3 equals 4 minus t, right? So what we can say about that set of vectors is that the set P1, P2, and P3, that set of vectors, polynomials, is linearly dependent. And then the reason that it's linearly dependent, because P3 equals 4 times P1 minus P2. So if I take 4 times P1, that is 4, minus P2, 4 minus t is P3. So that set of vectors, that set of polynomials, is linearly dependent. Okay, and then the next example, there's not much to do in this one. It's just kind of you can read the example type question. The set sine t comma cosine t, so that set of vectors is linearly dependent between 0 and 1, the set space of continuous functions for t's from 0 to 1, because sine t and cosine t are not multiples of each other as vectors in that interval. There is no scalar that maps the cosine of t onto c times the sine of t, so I can't make them map on top of each other. If I could, then they would be linearly dependent, but I can't, so they're linearly independent. Okay, and then the however there, that's an example of a set sine t cosine t comma sine 2t. Those are linearly dependent because there's the double angle identity that says that sine of 2t is 2 sine t cosine t, so that I can find that scalar that maps one onto the other. So that set in the second part is linearly dependent. So even though those two functions in that interval may not look the exact same, using a scalar I can map one onto the other, whereas I can't with sine t cosine t. All right, now we get to a definition. This is the main topic of this section, that is a basis. So they use a fancy B to write our basis, okay, but H is a subspace of a vector space, an index set of vectors, B1 through BP, so we're using B's in this for our basis, is a basis for H if B, my set, is linearly independent, and the subspace spanned by B coincides with H. That is, H is the span of that set of vectors. So if I can check off those two boxes, my basis is linearly independent and it spans my subspace, then it is a basis. Or if my set is linearly independent and spans the subspace, then B is called a basis for H. Okay, so that's the definition. That's the new term that we're encountering in this section. And in this next example that I'm just going to kind of write out, we're going to say let A be an invertible n by n matrix. So A has an inverse. And we're going to say A is equal to A1, A2, ... an. So A has n columns, right? And we're naming them A1 through AN. All right. Then we'll say then the columns of A, the columns of matrix A that I just kind of defined right above that, they form a basis, that's my new term, a basis for Rn, because what do we know about invertible matrices? Because those columns, they are linearly independent and they span Rn. And how do I know that? By the invertible matrix theorem. Okay, so if A is invertible, its columns are a basis for Rn. So an invertible 3 by 3 matrix, the columns are a basis for R3. An invertible 4 by 4 matrix, its columns are form a basis for R4. That's what that example says. And I know that because those are two of the conditions in the invertible matrix theorem. In the next example, again, this one, there's not a lot, there's no work that we have to do for this one, just the understanding. E1 through En, that set of vectors, those are the columns of the identity matrix. You know, 1 with a bunch of zeros below it, 0, 1, and a bunch of zeros below it, 0, 0, and then a 1 all the way at the bottom. Those are my E1 through En. The columns of the identity matrix, they form they are called the standard basis for Rn. The standard basis for Rn. That set of vectors, because they are clearly linearly independent and they span Rn. Okay, so that's called the standard basis. So in R3, I hat, j hat. Oops, let me write this a little bit more formally. In R3, the set I hat, comma, j hat, comma, k hat. That set is the standard basis for R3. 1 0 0 0 1 0 0 0 1 called the standard basis. All right, so how do we determine if we have a set of vectors? If they are a basis for R3. So the steps here, so I've got V1, V2, V3. Okay. Well, if I want to determine if it's a basis, I need to say, hey, are they linearly independent, and do they span R3? Now, there are multiple methods we could take to figure this out, but the method that I'll use is I'm going to say, I'm going to write these three vectors as a single matrix, -4, 1, 7, -2, 1, 5, and maybe I perform a couple of row operations on that matrix. I'll leave the first row the way it is. I'll leave the second row the way it is, and I want to double the first row and add the third row. So you double the 3 and -6 is 0, double the -4, add 7 is -1, double -2, add 5 is +1. All right, and then we do one more row operation, 3, -4, -2, 0, 1, 1, add rows 2 and 3, 0, 0, 2. Okay, so now we can see, all right, what are my pivots? I got a pivot, I got a pivot, I got a pivot. What does that mean about that matrix? Well, it's invertible. That matrix is invertible. T-I-B-L-E. Therefore, the set V1, V2, V3 are linearly independent. I'm going to abbreviate that. Linearly independent. And they span R3 by the invertible matrix theorem. So they are a basis. They are a basis for R3. Okay, so that's the process. So we're just kind of adding on a new piece of information, right? If I have these two boxes checked off, linearly independent and spanning, then we have this thing, this new thing that is called a basis. Okay, and now I know that it's a basis, I can generate all of R3, right? We can use those three vectors, linear combinations of those three vectors can give me any point in R3. In this next example, we're given a set s equal to 1 comma t squared all the way up through t to the nth power, and we have to verify that s is a basis for Pn, that is nth degree polynomials. And then if it is, this basis is called the standard basis for Pn. But how do we verify it's a basis? All right, so what I'm going to say first is s spans Pn. Okay, so how do I know that that is true? I'm stating it as, yep, that's true. But how do I know? Well, if I take linear combinations of that set of vectors, 1t, t squared, with different scalars, can I produce any polynomial that I want to up to an nth degree? Yes, I can. So that one, there's not a lot of work to do. We just kind of have to state it and recognize why it's true. Okay. So then for the second part, I need to show that it's linearly independent. So I'm going to say suppose, S-U-P-P-O-S-E, suppose C naught through Cn satisfy C naught times 1 plus C1 t plus C2 t squared, hopefully you get the idea there, plus etc. up to Cn t to the nth power, that's t, equals 0. Okay. When is that linear combination equal to 0? Well, this is true. If and only if, that's the abbreviation for if and only if, IFF. This is true if and only if C naught, C1, C2, all the way up to Cn are all 0. Okay, that's the only way for that linear combination to be 0. So S is a basis for nth degree polynomials. Okay, so we check off span pretty quickly and linear independence with just a little bit of thinking there. How do we know those vectors, those terms, are linearly independent? All right, now this next slide, we are introduced to, well, an example that will ultimately lead to the spanning set theorem. So in the example, we're given 3 vectors, v1, v2, v3, and defining h as the span of that set. And then we're also given the information that, well, they're not linearly independent. They're linearly dependent because we're told v3 equals 5v1 plus 3v2. So we're given that linear dependence relation, all right? And then it says to show that the span of the 3 vectors is equal to the span of just v1 and v2. And then it says find a basis for the subspace H. All right, so what does that look like? All right, so what we're going to do in this example now is we're going to say, or I'm going to say first, that every vector, so every vector in the span of just v1, v2, in the span of v1, comma v2, is also in H. Is in H. H being the span of the 3 vectors. Okay. How do I know that? Because, right, I'm stating it first and then giving my reason. C1v1 plus C2v2 is equal to C1v1 plus C2v2 plus 0 times v3. Basically, the argument that I'm making there is that I don't need V3 to produce H. H can be produced by just V1 and V2 because V3 is dependent upon those 2 vectors. The 3 vectors together are linearly dependent. Okay, and kind of to make that even more clear, hopefully, is I'm going to say let X be a vector. X be a vector in H. Let X be a vector in H, so the span of the 3 vectors. So X is equal to C1v1 plus C2v2 plus C3v3. Okay, so it's in all 3 vectors produce X. Well, maybe I don't need all 3 vectors, so I can make a substitution here. I'm going to say X equals C1v1 plus C2v2. Remember that linear dependence relation that we were given at the beginning of the problem? I can make a substitution here and say plus C3 times 5v1 plus 3v2. that is equal to v3. So I can substitute my dependence relation, which I can then rearrange, so I can take that C3 and substitute and move things around so that we have what'll end up being C1 plus 5C3 times V1 plus, what's my other one? C2 plus 3C3 times V2. So I substituted and I moved things around, okay? Take a look and, do the distribution and rearranging if you're not sure where I made, what leap I made in that step. So I can show that X, even though it's an H, I don't need my V3 vector to produce my vector X. So I'm going to say thus, X is in the span of just the two vectors. X is in the span of V1, V2, as is every vector in H. All right, so H and the span of V1, comma V2, they are the same set of vectors. They're the same set of vectors. And moreover, and V1, comma V2 form a basis for H, because they're linearly independent. I can check that the two vectors are linearly independent because they don't scale each other, but they form a basis for H. Okay, so that problem a little bit more involved, but the purpose of it is to introduce this idea that I don't need that extra vector I don't need that extra vector in my basis. We throw it out, we don't need it. And that's what really brings about this thing called the spanning set theorem. And here it is. So if I have a set of vectors, V1 through VP, so S is equal to V1 through VP, and they're set in a vector space V, H is their span. If one of the vectors in S is a linear combination of the others, of the remaining vectors, then the set formed by S, by removing that vector, so the vector that is a linear combination of the others, will throw it out, it still spans H. So I can remove vectors if they're linear combinations of the other ones and still span my subspace. If H is not equal to the zero subspace, then some subset of S is a basis for H. And that part B basically just says I can throw out enough vectors until I ultimately arrive at my basis. There is a proof of this theorem in the book. I encourage you to go read it. But really what it does in the proof is take the previous example, which is a specific concrete example, and generalizes it. And that's a cool contrast, I think, to see for upper-level math students, to see how we take a specific example, the previous slide, and generalize it to form an argument that is true for all sets. So I encourage you to do that, but I'm not going to do the proof here. In the next two examples, we look at bases for the null and column space of a matrix A. In this first one, we're looking at specifically a basis for the column space. Okay, and what we can see in this example, that we have a matrix that's in reduced echelon form. So there's zeros below the ones, zeros above the ones, the pivots, and a row of zeros at the bottom. Okay, so what we can say is, or what I'm going to say is that the non-pivot columns are linear combinations, so I'm reading that LC, are linear combinations of the pivot columns. Okay, and I'll give you an example. This column right here is 4 times that column right there. Linear combination. This column right here is a linear combination of that one and that one. It's 2 times the first column plus the third column. Okay, so that's what I mean by that sentence that I just wrote down. All right, and actually maybe I'll even write it down. So I will say B2 is equal to 4 times B1, and B4 is double B1 minus B3. So what do? So discard them. Throw them out. Discard them. And I didn't write this, but let me just throw my labels on here. This guy is B1, B2, B3, B4, B5. Okay. So the argument then in discarding those three columns is that the set B1, B3, B5, that set still spans the column space of my matrix B. Okay, so S is equal to, so my basis is equal to the vector 1, 0, 0, 0, the vector 0, 1, 0, 0, and the vector 0, 0, 1, 0. Okay, that's a basis for the column space. In this next example 9, we're given a much more ugly looking matrix that is not in echelon or reduced echelon form. So we have this matrix A, and they tell us, though, that it is row equivalent. That's a terrible underlining. It is row equivalent to the matrix from example 8, from the previous example, so the one that we just had. Okay, and it says find a basis for the column space. Now, knowing that they are row equivalent to each other, right, this is row equivalent to the previous example 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, 2, minus 1, 0, 0, 0, 0, 1, 0. That is row equivalent to the previous, the matrix from the previous example, right? And I have pivots in column 1, column 3, and column 5. 1, 2, 3, 4, 5. Yes, I have those 3 pivots there. And it says find a basis for the column space of this matrix A. Well, because I know that it reduces to what I've got written there, I could say that the columns A1, A3, and A5, that's this one, and that one, A1, A2, A3, A4, A5. But those 3 columns, that set is a basis for the column space of A. Because I know that it reduces the way that it does, those are the 3 columns where I end up with pivots. So those 3 columns are linearly independent of each other. Those 3 vectors are linearly independent of each other. And again, just to add a little bit more emphasis, I know that this is a basis for the column space because AX equals 0 and BX equals 0 have the same solution. They have the same solution and the same linear dependence relation. And you could even go ahead and check. Column 2 is 4 times column 1, as it was in the previous example. Then those two examples generalize to theorem 6 that says the pivot columns of a matrix form a basis for its column space. Okay, so that just takes the 2 examples that we looked at and puts them in a general way. This proof is also in your book. I'm not going to do it in class, but I would encourage you to read it and understand the argument that it makes. All right, and then finally we get one more example. This one, there's not a lot of work to do here. We'll kind of treat it as a matching example. And it says the following, we have 3 sets in R3. And if you notice, they're similar. The first set, the second set adds on a vector. The third set adds on one more vector. They show how a linearly independent set can be enlarged to a basis, and how further enlargement, and I love the use of the word destroys, it destroys the linear independence of the set. A spanning set can be shrunk to a basis, but further shrinking destroys the spanning proper, that's probably the word property, it just got cut off there. All right, so what does that mean? All right, so which of those 3 sets, and I'll start with this one, which of those 3 sets form a basis for R3? This one, this one, this one. Well, maybe you know it's that one. Hopefully you know it's that one. It's a basis for R3 because they're linearly independent, and they span R3 because I have 3 pivots It's not this one because I don't have enough pivots, and it's not that one because I know that those are linearly dependent, right? I couldn't one of those vectors can be formed out of the other three. Okay, I have a free variable. All right, so that guy goes on this one. All right, so which ones are linearly which set is linearly independent but does not span R3? Well, maybe you can tell it's that one. Those two vectors, they don't scale each other, so they're linearly independent, but I can only get a plane in R3, not all of R3. And then this last guy spans R3. Those four vectors definitely span R3, but they are linearly dependent. I could form this fourth vector, this guy, using the other three vectors. Okay, and then going back to this idea of destroying a linearly independent set, that's this one, can be enlarged to a basis, and further enlargement destroys the linear independence. And then a spanning set can be shrunk to a basis, but further shrinking destroys the spanning property. That's what's going on there. All right, that's the end of that section. Thank you for listening.